This is ISO 376 Explained. My name is Henry Zumbrun, president of Morehouse Instrument Company. I've been with Morehouse since 1999, so we're coming up on 20 years pretty soon. And as I said before, please feel free to use the chat to ask any questions during the webinar, which will be answered at the end of it. And feel free to contact me at any time. What we do, we are a manufacturing company that produces force calibration equipment and adapters that are used in industry to measure force. We have force and torque calibration laboratories and offer calibrations at a very high level of accuracy. We have force capabilities up to 120,000 pounds of about 20 parts per million, and other force calibrations are offered up to 10 meganewtons or 2.25 million pounds, known to within about 100 parts per million. On the torque side of things, we bought the standard from NPL United Kingdom. We do calibrations in accordance with ASTM E74 28 with other standards, BS7882, which we may be dropping because there's just not a lot of BS7882 work coming to this country. And that's kind of similar to how ISO 376 works, with the exception of every year we're doing more and more ISO 376 calibrations. So there are requirements, and people are asking for it. But BS 7882, we've had that on our scope for years, and we get like one requirement every 3 or 4 years. So may not be a standard that we keep up for torque. This standard was bought by, from an NMI. It's probably the second most accurate torque standard in the world. With that said, that's a brief introduction on us. Let's start with what's going on with ISO 376 and what we're going to cover today. We're going to cover the ISO 376 standard requirements. There are some interesting ones in there that people miss. Lots of labs continue to miss. We're going to discuss why ASTM E74 is not ISO 376. We have a full paper coming out in CalLab. You can look that up. Probably the next issue of CalLab's going to have it. We have 4 blogs currently on our website on ISO 376 if you want to read more or learn more about ISO 376. And then we're also going to discuss ISO 376 adapter recommendations. The standard does a fantastic job in the annex of recommending good adapters for force measurement. And that's something I'm very, very passionate about, because you can do all the right things, and if you fail to get the adapters right, there's going to be errors. In some cases, those errors are 20 times higher than what your expected calibration result is, just from switching top pads, using the wrong pins, doing things that, the labs that are not really what the lab's doing during calibration. I mean, when we do a calibration, we hope to replicate how the customer is using the instrumentation. If we fail to do that and the customer fails to, use the instrument the way we said we calibrated it, there's very, very large errors. ISO does a fantastic job at the end, which we will talk about, of diving into those and trying to ensure that results are repeatable. And then a little bit at the end, calculating force CMCs per ISO 376. This is nowhere near as involved as it needs to be. We have a Excel spreadsheet that can be downloaded that you just plug in the stuff from the ISO certificate. So talking about the ISO 376 standard, the current version is 2001, and the full name is Metallic Materials Calibration of Force Proving Instruments Used for the Verification of Uniaxial Testing Machines is used for. Basically, the highlighted section is what we're using these for, to calibrate testing machines to the ISO 7500 standard. And it's also used to calibrate other force-proving instruments to ISO 376. In part of what is a force-proving instrument? It's a whole assembly from the force transducer through to and including the indicator. So it's the whole system. Always recommend that, if you're using a device with an indicator, that you send everything in for calibration. You send the device with the indicator, with everything you're using, and it can be calibrated as a full system. This includes cables. And ISO does an interesting job. I've seen this in the ISO 376 standard and also in the Australian standard. Characterization of force-proving instruments. under 6.1 identification, all elements of the force proving instrument, including the cables for electrical connection, shall be individually and uniquely identified, e.g. by the name of the manufacturer, the model, and serial number. For the force transducer, the maximum working force shall be indicated. This is probably, if you're an auditor, this is probably the #1 deficiency on this standard if you wanted to write people up with. I've yet to see people have a lot of their cables labeled and serial numbered. It is very, very rare working in our lab that we see a full system come in with serial numbers on the cables. Section 6.2 says application of force. The force transducer and its loading fittings shall be designed so as to ensure axial application of force, whether it's tension or compression. We'll get into more of that in a bit later when we discuss the annex. And then we have the calibration procedure, which is probably why most people are here. Section 0.1 starts the calibration procedure and says, ensure that the attachment system of the force proving instrument allows actual application of force when the instrument is used for tensile testing, and that no interaction between the force transducer and its support on the calibration machine when the instrument is used for compression testing. Picture above, this is a multi-axis load cell in our calibrating machine. When we discuss these adapters, we have sphericals. 2 sets of sphericals in where I'm highlighting in line with this to help ensure that the force is applied in the axial orientation. And then in compression here, we use a hardened ball adapter, and this is in our dead weight frame. It's a ball clip and a Morehouse ultra precision cell flat on a block for compression. So ISO defines, the reason I put this part in here is for section 7.2 resolution. Those familiar with ISO M3003, ISO 1725, some other standards that talk about resolution, what resolution is. ISO 376 allows a little bit different than what people are used to. And if you look at this, it says the resolution R of the indicator shall be obtained from the ratio between the width of the pointer and the center to center distance between 2 adjacent scale graduation marks, scale interval. The recommended ratios being 1/2, 1/5, 1/10. A spacing, and then it defines a spacing of 1.25 millimeters or greater required for the estimation of 1/10 of a division on the scale. So a little bit different than what most people are accustomed. You can go to, 1/2, 1/5, or 1/10. A lot of people would look at this gauge and say, hey, you can only read this to 1/2. The way I'm interpreting this is you can read it beyond that for that standard, and ASTM is the same way in that regard. And then a digital scale, this is common for everything. The resolution is considered to be 1 increment of the last active number on the numerical indicator. If the reading fluctuates with no force applied, the resolution will be the fluctuation divided by 2. So if right now that could be reading by 0.1, it could be reading by 0.5. If that were fluctuating between 0.1 and 0.5, we'd have to divide that by 2 and say, hey, this is 2.5 or 3. Some other things about ISO 376, minimum force. ISO 376 uses a class system. ASTM has 2 things. When we look at, if you're familiar with ASTM, they have class AA and class A ranges. ISO has 4 ranges. And these ranges are 4,000 times the resolution. The minimum force shall be greater than or equal to 4,000 times the resolution for class 00, 2,000 for class half, 1,000 for class 1, 500 for class. That should be class 2. I got a mistake here. But 500 for class 2. The minimum force shall be greater or equal to 2% of the maximum calibration force applied. So if we look at this, if I have a 2,000-pound load cell and indicator have a resolution of, let's say, 0.005 pounds, the first test for the class 00 range cannot be less than 40 pounds, which is 2%, even though 0.005 times 4,000 equals 20 pounds. This is something that's important. ISO says, hey, you're not going over, you're not going under 2%. ASTM has a recommendation that you can go under 2%. It's recommended that it be 2%, but you can go under. So ISO is basically saying nope on 2%. So you have these two criteria to use to determine the minimum force. Calibration procedure per section 7.4.1. Before the calibration forces are applied in a given mode, tension or compression, the maximum force shall be applied to the instrument 3 times. The duration of the application of each preload shall be between 60 and 90 seconds. The only thing different here is ASTM requires only 2 exercise cycles, though most calibration labs, and we recommend it to them, perform at least 3. It's just good practice. On the selection of forces, so we're gonna, if we want to do an instrument that's, calibrate an instrument and assign a class 00 range, we're gonna take 4,000 times the resolution. Typically what happens though is when you're trying to meet all the other classes, you may not meet the class 00 down at that 2% point. So knowing that, our typical suggestion is, we have a 5,000 pound cell here. Our typical selection is 4,000 times the resolution as our first point if we know the customer wants a class 00, and a 5% point. And then we try to select a point around every 10% through the 100% of the range. We do this because if the instrument does not meet class 00 at 2%, it's not going to meet then if we don't take that 5% point till probably 10%. And that's from that 2% to 10%, you cannot use it in that class 00 or class 00 range. So we take a 5% point, and in most cases, the instrument will meet at the 5% point if it's a good load cell or good force indicating instrument. ISO 7.4.2 procedure. Important to note here, I'm showing you 12. That's our recommendation because we've done a lot of these calibrations and we want to give the best possible loading range to our customers. But the actual procedure says requires at least 8 forces, and they shall be distributed as uniformly as possible over the loading range. So we select our forces. And then we get to the procedure. And the procedure in 7.4.2 is carry out the calibration by applying 2 series of calibration forces to the force proving instrument with increasing values only, without disturbing the device. 0 degree orientation, X1 and X2. That's down here. That data is going to be used to test just repeatability only. So we're going to take the instrument, we've already exercised it, and then we're going to put it in the 0 position. And then we're going to do our 8 to 12 forces. Remember, we recommend 12, ISO only requires 8. And then we're going to do them a second time without disturbing the instrument. And that's going to give us our X1 and X2 value. Then we're going to apply 2 further series of increasing, and if the force proving instrument is to be calibrated in incremental, decremental loading directions, decreasing values. Between each of the further series of forces, rotate the force proving instrument symmetrically on its axis to position uniformly distributed over 360, namely 0, 120, 240. If this is not possible, it is permissible to adopt the following positions, 0, 180, and 360. So basically here, we're going to move the instrument. If we're doing decremental loads and we're going to test for reversibility, we're going to do an increasing and decreasing load at X5 and X6, and we're going to do an increasing and decreasing load at X3 and X4. If we're doing increasing values only, we're just going to do X3 and X5. So the X4 and the X6 is for decreasing. And I'll show an example a little bit later on that with ascending calibration. So for 7.4.2, the interpolation curve shall be determined from the average of deflections with rotation XR as defined in 7.5.1. So if we go and look at 7.5.1, that's basically going to tell us that we can use a first, second, or third order equation. And that's important to note because other standards allow higher order equations where ISO limits it per that section to just a 3rd degree only. This procedure determines only a combined value of hysteresis of the device and the calibration machine, and then accurate determination of hysteresis of the device may be performed on deadweight machines. For other types of calibration machines, their hysteresis should be considered. So this is if you're doing descending loading on that X4 and X6 curve. So again, time interval. If we look at the time interval between two successive loadings, ISO says it shall be as uniform as possible, and no reading shall be taken within 30 seconds of the start of the force. This is interesting because lots of people using transfer standards or using the cow machines, the automated cow machines with servo controls and hydraulics, the machine just ramps right up, takes readings, and ramps right down. So to do a calibration with ISO, a lot of times we'll break that machine, or that machine will not be capable of doing that calibration because you actually have to hold the force for at least 30 seconds at each test point. ASTM does not address this. We've adopted for all of our calibrations, because it's just general good measurement practice, to take at least a dwell time of 30 seconds and then start taking the readings, especially with static force. And if you're sending your equipment to a lab that's just going up and going down and they're not waiting 30 seconds, they are not following the ISO 376 standards. So the other part of the standard, the calibration shall be performed at a temperature stable to within plus or minus 1 degree C. This is the same as E74. This temperature shall be within the range of 18 degrees C to 28 degrees C and shall be recorded. Sufficient time shall be allowed for the force proving instrument to attain stable temperature. That's typically on the end user, the mass of the material, everything else that will determine how long an instrument needs to acclimate to room temperature. Strain gauge transducers shall be energized for at least 30 minutes before calibration. This is good practice anyway to warm up the equipment, to get the signal if you're using 5 volts, 10 volts excitation, to get everything warm and have everything electrically stabilized. Creep test. If the force proving instrument is to be calibrated in incremental only loading direction. So if we're not doing reversibility, we're not doing the X4 and X6 calibration, six really sets of data, we're going to have to do a creep test. And to do the creep test, we're going to record its output at 30 seconds and basically 5 minutes, 300 seconds after application or removal of the maximum calibration force. In each mode of force application, to enable its creep characteristics to be determined, if creep is to be measured at 0 force, the maximum calibration force shall be maintained for at least 60 seconds prior to its removal. The creep test may be performed at any time after preloading during the calibration procedure. So we're going to get into that. It's a lot to process right now. We're going to get into that in a little more detail. So on the certificate, ISO requires the method of creep measurement, creep at maximum force or after force removal. When the creep measurement was performed after preloading, after the last measurement series, the length of time at which the force was applied prior to removal for creep determination of force. And then you get down here and you look at our certificate and you say here, force held at max force for 90 seconds, output 30 seconds was, negative 0.00002, output after 300 seconds. There's a formula to do this error, class assignment here. And then at the end, lots of labs miss this as well, this requirement to report on the certificate, which is creep test was performed after the last measurement series. So example of data for increasing forces only. We are at X0, X1, X3, and X5. So this is this is what our Excel sheet, yes, we are using Excel to do our 376 calibrations. This is what our Excel sheet looks like. We enter in all of this information, the starting temp, the ending temp, the force applied, the calibration standard over here, the runs, run 2, 3, these are all increasing because we're doing a creep test down here. So we enter all this information in, and then we start doing data analysis. And ISO is very interesting in the data analysis section because it tests the device for numerous things. We test for here, this is directly from the standard table 2 characteristics of force proving instruments. We test for reproducibility. We test for repeatability. We test error of interpolation. We test of 0. And then here's reversibility, but remember, reversibility is only if the instrument is going to be used that way. If it's going to be used to take descending measurements. If it's not used to take descending measurements, then you do a creep test instead. So this is really one or the other. And then ISO does a nice job, very nice job in the standard of expanded uncertainty of the applied calibration force. So if I have an applied calibration force with an expanded uncertainty of greater than 0.1, I cannot assign a class 00 loading range. If I have one greater than 0.2, I cannot assign a class half. So if you look at people's scopes of accreditation and they're saying, hey, I'm 0.04, then guess what? The best they can do is going to be class half, because 0.4 is between the 0.2 and 0.5. If they're saying they're at 0.5, there's a good chance that the best they can do is only class 1. So it's depending on what you need. Typically, if you're calibrating other load cells and you want to continue calibrating in accordance with ISO 376, you're going to need class 00 ranges. And then the next, you're going to do your uncertainty, and pretty much the next calibration is going to be class half. They're going to do their calibration, and hopefully that it's going to be 1 or 2. So really nicely takes care of that measurement traceability and the uncertain metrological traceability in regards to uncertainty. This standard does a very good job with that. So assessment of the force proving instrument, relative reproducibility and repeatability errors, called B. And so how you calculate them: repeatability errors calculated by taking the average reading of the first 2 positions, then taking the difference of x2 minus x1 divided by the average times 100. Reproducibility is found by taking the average of x1, x3, and x5, then take the maximum difference divided by the average times 100. I'm going through this rather quickly, and you can download this the PDF and go through it. Then we have interpolation error. This error is determined using first, second, or third degree equation, given the deflection XR as a function of the calibration force. That's how you calculate that. Relative zero error. The error is determined by taking the zero reading before forces have been applied minus the zero reading after force has been applied, and dividing by the deflection corresponding to the maximum calibration force, and then multiplying this by 100. Then you have reversibility error. This is, if you're doing this, it's only at x4 and x6. The descending measurements, and it's found by using these equations, and then you report the average value. There's creep error. Creep error is found by taking the difference in outputs obtained 30 seconds and 5 minutes, taking those differences. And then you do all of that math, and then you can classify the force proving instrument. And ISO has 4 cases for classification. Case A and B are for specific force devices, which are specific meaning only used at the forces that they were tested at. Case A then is for incremental loading only, and case B is for incremental and decremental loading. Most people are going to be using case C and D, instruments classified for interpolation. Case C is what we see the most of. It's for incremental loading only, and case B is for incremental and decremental loading. So again, case C is you do the creep test, and we see that the most. There's the table again. So we're going to go through all these cases. If you're doing a cert, if you have reproducibility is 0.4, that's good. Repeatability, say, is at 0.5. Interpolation is at 0.25. Percent of zero is at 0.25. Say we did reversibilities at 0.7, and our calibration force was better than 0.1. According to ISO 376, the best this instrument can be is class half for the range of use. So, and I want to try to clarify that here. So if this were at the 2% point, we got these numbers, then at 2% it would be class half. Now at a 10% point, if we got different numbers, at 10% it could go to class 00. If this were at the 10% point, if these were the numbers, the best it could be is class half. So every point is checked in line. And say, for instance, we got an interpolation error of 0.2 down here. Even though class 0, class half for maybe all the other errors in the chart, the worst one will determine the class.
So I hope that made sense. Here's an example of our cert. So our cert page 1, class 00, 100 to 500. We look at the data, we have the force, we have the serial number of the machine used, we have our data spread. You can see what each of the runs are doing and how they're performing. I wanted to call out max uncertainty using the equation from ISO. We're using that max uncertainty equation, and we're saying it's 0.01% of applied. That could be at the 2% point. So classifications typically appear on the first page of the certificate. The Morehouse Ultra Precision Load Cell passes class 00 requirements from 100 to 5,000 pounds, with right there with 0.017% of applied. So if we go and use this cell, max uncertainty, the best we're going to be able to do is do a class half calibration with it, with that, if we're using that max uncertainty. So, and then I have an example of a non-Morehouse cell. This is pretty typical, a cell sent into us for calibration. And I was trying to explain what that range. Whoops. So trying to explain with that range there. Trying to explain with that range there, the classification and some of the other stuff that's going on. So class half in this situation was 17.793 to 302.478 kilonewtons with a max expanded uncertainty 0.076. But then if you look at class 1, the class 1 loading range is greater. They can use this instrument can be used lower, at lower capacities if they meet class 1, and at higher capacities for class half. And if you look at the max expanded uncertainties, 0.076, 0.156, 0.092 in tension, and 0.209 versus this up here, the 0.017. So this cell, realistically, this cell is suitable for ISO 7500 calibration. They're probably not going to calibrate many other instruments in accordance with ISO 376 with these types of ranges. Looking at the data in more detail, here's more information, compression calibration data on our CERT, polynomial equations. ISO only allows up to a 1/3 degree, so that's all we can use. They may be better at a 1/5, but it doesn't allow it. And then the page 4 of the CERT has all the classes. And if you look through here, you can see repeatability with rotation. Here's all class 00, repeatability without class, fit error, resolution. It tests for resolution, uncertainty of the machine, class 0, zero error down here, all 00s, creep, all 00s. And then an expanded uncertainty equation is reported, which is nice. So you can use this equation for the expanded uncertainty at any point during the force range, and it will tell you what your actual uncertainty is. So if you're issuing reports to customers or you're out in the field and you're using an ISO calibration, you will know your expanded uncertainty per ISO 376. And if we look at these in higher detail, you can see the actual numbers, 0.01, 0.004 per point. As I said, every one is tested per the load point, and this is why that 5% point is recommended. And if I can talk about that, try to talk about that in more detail. If this were to say class half instead of class 00, and the next point we did was at 500 pounds, the range assignment would be class 00 from 500. And that's why we like to do the 5% point. If I had a better example with a class half here and then class 00 here, you'd see that, yeah, I may be able to use this cell from 5% to 100% at class 00. So there's a bigger picture of all the uncertainty. And then there's the 0, the creep results, and then more on this expanded uncertainty equation. So you can use this equation. If you want to know what the uncertainty is at 300 pounds, this is a 5,000 pound device, you can use this equation. And then we get to the point of reporting. I just showed you our typical certificate for ISO 377, the Morehouse certificate for ISO 376, but ISO 376 has additional requirements. Maximum period of validity is 26 months.
Identify the reference standard in all elements of the force proving system. That's cables and everything else, top locks if they're included with serial numbers, everything. The mode of force application, tension, compression, that the instrument is in accordance with the requirements of preliminary test, the class and range of validity, the date and interpolation equation, which you saw that was a 3rd degree, the temperature at which the calibration was performed, the uncertainty of the calibration results, and then, if needed, the details of the creep measurement, which is when you did the creep test, what the results were. And if we start looking at expanded uncertainty, so this is the 5,000 pound cell we did, the points, millivolt values, and you can see the expanded uncertainty of this cell ranges at that 100 pound 2% first test point at 0.0164 to at capacity 0.369. So if we're calibrating expanded uncertainty in accordance with the ISO 376 standard, we're going to have, there's 8 things that we must consider per the standard. There are additional things to consider, certainly, but there's 8 that are built into it. It's the relative standard uncertainty associated with applied calibration force. As I said, this one's my favorite for 2 reasons, because one, the majority of the time we're using dead weights and we can give very, very low numbers. But the second is it follows that metrological traceability pyramid where the uncertainty of the reference standard must be included. And the standard does it for you. It requires it in the standard instead of outside of the standard, where you can have someone having an expanded uncertainty of 0.05 giving you measurement uncertainty of less than that when you just use the ASTM lower limit factor only. So then you have the relative standard associated with the reproducibility, uncertainty associated with repeatability, resolution of the indicator, creep if you're not doing reversibility, drift and 0 output, temperature, and then interpolation. If this were a reversibility, creep will be replaced with that. So ASTM, I've been talking about it throughout the webinar. ASTM is not ISO 376. I like this drawing. It is kind of comparing apples to oranges. There are similarities, but they're way too different to say I can go use an ASTM calibration to certify something to ISO 376. So the ISO 7501 calibration and verification of static uniaxial testing machines requires standards to be calibrated in accordance with ISO 376. One cannot use ASTM E74 calibration to perform an ISO 7500 calibration. ISO 376 has several requirements that are not requirements of ASTM E74. There's all the characteristics again. If you look at them, these are just not in E74. Reproducibility, repeatability, interpolation, reversibility, creep, calibration standard, not there. What is in ASTM E74 is a procedure that calculates the lower limit factor based on a series of measurements in which the standard deviation from the predicted response is calculated. It's fairly simple. We're going to calculate the standard deviation. We're going to rotate the instrument like we did in ISO. That's 0, 120, and 240 is recommended. We report the resolution, the lower limit factor, and then we assign a range. In this situation, it's just class A or double A, depending on what's going on. You can see you're not getting uncertainties, you're not getting anything else. You're basically getting an expected performance of that device when you go and use the same type of fixtures and everything else when you go and use that in your equipment or to calibrate a testing machine. ASTM defines primary and secondary standards. Primary standards are dead weights. They are required to assign a class AA loading range. They are adjusted for local gravity, air buoyancy. They must be adjusted to 50 parts per million or better. Most weights, we're just doing a set now for a customer, and we put on the PO to Tromner, to Heuser, who are now Mettler Toledo or Rice Lake. We put on the PO, or even NIST. NIST is of course the best, but they also have long lead times and they are very expensive. They're about 80 grand for a typical machine just to calibrate weights. So if you have the money and want the best, NIST is the best. But for the typical calibrations, most state labs can even do 10 to 20 parts per million. We put all our, when we do weights for people, we have them adjusted. Right now we're getting ready to send weights to Mettler, and they'll be adjusted to within 10 parts per million. And they are made, weights shall be made of rolled, forged, or cast metal. Typically, we're going to do stainless steel if it's a small weight. It's the preferred material because of it does not rust and it is not magnetic. So secondary force standard, those are the standards. There's some examples. Instrument or mechanism of calibration which has been established by comparison with primary standards. You have load cells, proving rings, and then you have lever amplification machines. In order to perform calibrations in accordance with ASTM E74, your force standard must be calibrated with primary standards. So secondary standard as defined is class AA loading range for calibration is 2,000 times the lower limit factor, which gives a 5-to-1 ratio. And then those devices or dead weights can be used to assign a class A loading range, which gives a 4-to-1 ratio on the testing machine. So basically what I'm saying here is ASTM requirements, it's using TAR, test accuracy ratios, 50 parts per million, or 0.005%, 0.05%, 0.25, and then 1%. So at the end of this, it's a closed system working with TARs to ensure that the TAR is 4 times better than the testing machine, and then that the secondary standards are 5 times better than the working, and that the primary standards are 10 times better than the secondary. Now here's how what ISO 376 done. It's more in line with that metrological traceability and uncertainty. So the plus minus 0.01 if you have a uncertainty of better than 0.01, you can certify a device to class 00, usually requires dead weight primary standards. And if a standard is used close to 0.01, the calibration will mostly bump to class half at best, because there are lots of other things to consider. So the way this propagates is 0.01 class 00, 0.02 class half, 0.05 class 1, and then 0.1 class 2. So certifying the device to class 2 usually requires a force proving instrument that's class 1 or better. So usually you need a class 1 or better to certify class 2, obviously. Usually a class half is what's typically required. And then there's a nice write-up at the end of this. If you haven't read it and you're interested to learn a lot more about ISO 376 besides reading the standard, I recommend, it's free to download, Euromet CG4 version 2. And that describes the difference really between ASTM and ISO 376. It gives a nice write-up here. The calculation of uncertainty only includes contributions due to reproducibility and deviation from the interpolation equation. The uncertainty calculated by this method, they're talking about ASTM, ignores some of the components included in section 6.1. As such, is likely to result in different and probably lower values. And then the contributors due to the other uncertainty components present during the calibration should also be included. Recommendation, it's basically saying that ASTM is missing several things that ISO does have as far as uncertainty. So when you get a cal with ASTM E74 by rights, you have a little more work to do to quantify all the additional error sources. And then ISO addresses adapters, and using proper adapters when calibrating force instruments. Improper adapters can produce errors 10 to 20 times that of manufacturer stated accuracy. Proper alignment of the UUT, unit under test, adapters and proper methods for loading threads, misalignment, different hardness of adapters, thread loading versus shoulder loading, all contribute to a decrease in the repeatability of the measurement results, resulting in additional measurement error. Repeatability and reproducibility tests, as well as proficiency tests, are good methods for detecting additional measurement errors. So if we go back to ISO 376 and just general any force calibration that you do or that your lab is making or you're conducting, the importance of adapters is keeping the line of force pure, free from eccentric forces, is key to calibration of any load cell or any force proving instrument. ASTM E74 does not address the various adapters types, but ISO 376 does give guidance. More on the importance of adapters, which a lot of people tend to not realize, because they send us their load cells without top or bottom adapters, and that can be problematic. And the reason it can be problematic is material with different hardness experience different amounts of lateral deflection under the same amount of load. This causes different amounts of stress between the block and the load cell. The right adapters can eliminate these errors that could be as high as 0.5%. I've done numerous tests with this. Hard blocks, the hardness of the material makes a huge impact on several cells. ISO is going to recommend top adapters. If just general good practice is to have a top adapter for that load cell, and that's what's in red up here. So have a top adapter that's sent in with that cell, and then have it calibrated with that, because you're going to harden that material. If it's soft material, over the lifespan of it, you're going to harden it. It should stay with the load cell. Our preferred, if we're making a top block, we're sending it out to be heat treated to give better safety factors, and it makes the results much more reproducibility as far as rotation. We get much better numbers if we use a hardened adapter on the top of the load cell. ISO 376, we'll talk about their recommendation for compression adapters, but first we're going to talk about tension adapters. Here's a drawing of a quick change tension adapter, and it says ISO 376 recognizes the importance of adapters in reproducibility conditions of the measurement. Proper adapter use in accordance with ISO 376 Annex A helps ensure the reliability of reported measurements. Annex A is not a requirement for labs to adhere to. It's just a recommendation, but it's a very, very good one. And in general, the Annex A 4.1, load fittings should be designed in such a way that the line of force application is not distorted. Again, keeping that line of force pure from eccentric loads. As a rule, tensile force transducers should be fitted with 2-ball nuts, 2-ball cups, and if necessary, with 2 intermediate rings, while compressive force transducers should be fitted with 1 or 2 compression pads. So here's some pictures of adapters. We've adopted ISO 376 here. If you look at this, this is our quick change tension member adapters. In most cases, there's a spherical here, and there's a spherical down here, here, and here. Here's shown with a clevis, probably an ED dynamometer, where if you've seen our other webinars, you know the pin size in these makes a huge difference. But in any case, this adapter system, not only for load cells, but for other, clevises, with the clevis set for other, dynamometers, crane scales, whatever, will keep that line of force as pure as it can be. So there's better pictures of the adapters and what's going on. There's the spherical here, spherical down below, actual picture, and tensile force transducer should be fitted with 2-ball nuts and 2-ball cups. And then we have an adapter page, all the various pictures of adapters. We call these quick change tension member adapters. You have them here for clevises. You have them here for tension load cells. If you're operating a Cal lab, it's real easy to have one set of adapters here, TMAs, with some threaded adapters, and then a clevis set. And most likely anything that walks in your door, if you get enough of these adapters, you have them, and you actually know what you're using, where you can tell the customer and report it. So compressive force, I get a question come through, and of course I'm going to add, do we sell adapters? Yeah, these are pictures of all the adapters that we make, and we have catalogs, and we sell quite a bit of adapters, try to meet any customer's needs on adapters. So these are examples of the ones that we have and that they are available for sale. So then we talk about compression adapters. Compressive force transducers should be fitted with 1 or 2 compression pads. Here's the drawings for ISO 376. This is a recommendation, and then here's one that we came up with that we've provided. The top stud of the load cell, and then you have a top compression adapter here that's very similar to what's going on here. And then right here we're saying DUT with test instrument, device under test, unit under test, lots of names for it. So yes, we also have compression adapters. The tension ones are much, the results are much greater with the tension ones as far as improvements. But the compression ones, again, if you're using an adapter that's a different hardness than what the lab's using, you could be off, the measurement could be off by 0.5% on some load cells. Additional ISO 376 recommendations. Overload test, manufacturer should apply 8 to 12% overload for at least 60 seconds. Bearing pad test. This one's an interesting test. If you're using critical applications or you want to know how good your load cell is, this test is for verifying that there is no interaction between the force transducer of an instrument used in compression and its support on the calibration machine. The concave and convex surfaces are considered as representing the limits of absence of flatness and variations in hardness of the bearing pads on which the instrument could be used when in operation. The intermediate bearing pads are made of steel having a hardness between 400 HV30 and 650 HV30. The convexity and concavity of the surfaces are 1 plus or minus 0.1 in 1,000 and a radius of 0.1 plus or minus 0.01% of the radius. So for each force, the difference between the mean and deflection using concave and plane bearing pads and the difference between the mean deflection using convex and plane bearing pads should not exceed the limits given in table B1 in relation to the class of the force proving instrument, which is very interesting. So you do everything else. The annex is optional. You do everything else and your device could fail the bearing pad test, which means it's not really fit for use for the class 00. So we can perform bearing pad tests, and the test is often only ever required once per load cell. Load cells usually do not change. The test really, what this test does, I read a lot of wording, and what it really does is says the test will confirm the device is not too sensitive to surfaces that are not flat. And let's face it, in the dimensional world, everything is jello and nothing is flat. In our world, things are relatively flat, but you do have occasions where they're not, and a bearing pad test may be something you want to consider. So guidance documents, we're getting into the CMC section. Guidance documents that are available, you have NCSLI RP12. That's going to do nothing for you as far as ISO 376 is concerned. It's just there. I recommend it. And you have Euromet CG4, which I quoted earlier in the one section. I highly recommend, free to download. Anybody read Euromet CG4 if they're doing ISO 376 calibration. It's very, very complete. It may even be overly complete, but it's a fantastic document. And then we're working on a guidance document that was given to A2LA. Our guidance document has 4 cases. It has ASTM. It has those devices, load cells, nonlinearity, devices that are used to further disseminate force. And then it has devices like crane scales where they're the end of the line. You're just going to weigh something that's going to go on a truck or something else. And then for ISO 376, I was a bit snarky when I wrote it, and I just said, hey, see Euromet CG4, uncertainty of force measurements, because that's really anybody doing calibration in accordance with ISO 376 should be using that Euromet guide. But anyway, so you want to calculate force CMCs, Euromet CG4. We went over these before. All these, we give on our certificate an uncertainty equation. What you can do is you can take this equation and plug it into our Excel sheet, which I will talk to later. But Euromet CG4 is going to say resolution, contribution of all these, reversibility. What's interesting, and we didn't cover these, being used at different temperature, being used with different end loading conditions, effect of being used with different parasitic components. That bearing pad test is nice there. A different time loading profile. Again, if the lab, you're going to a company that's just taking up and down readings and does not have a dwell time, or just doing like 1 or 2 seconds as opposed to 30 seconds, there's going to be a difference in output. I have a little presentation I gave to E74 committee on that, and at times it can be significant. So effective linear approximations to interpolation equation, if applicable, effective replacement indicator, dynamic nature of the force being used there. That's very hard to quantify, but they put it in there. As I said, they put lots of things in there. But getting to our guide, so you've got a calibration in accordance with E74 or 376 or something else. We have an uncertainty guidance document that I can share with anybody. But if you've got it in accordance with ISO 376, you enter your equation here. Here you're going to want to, here you would select ISO 376. Right here it still says ASTM E74 LLF. This is just a general screenshot of all the different things that can be done. But you add this equation in here. There's a drop down over here. You can select ISO 376, and then you can conform with A2. This conforms with A2LA's R205 requirements and a lot of this Euromet CG4 requirements. So Euromet CG4 has a few additionals as with the other error sources, but we give that. You can put the miscellaneous error in here. So if anybody wants this, they're going to get a PDF later. It will have the link where you can go download this. The red tabs, when you look at these red tabs up here that I'm highlighting, they will call out exactly what's going on, what it's being used for, and give you more guidance than what I'm giving you right now. It would take quite a bit to go through all the ins and outs of uncertainty. But so if we're looking at uncertainty and we're breaking it down to type A and type B, this is normally the GUM. This is a combination of the GUM and R205, and some of the things that we need. The type A, the uncertainty equation from ISO 376 calibration, if we're doing R205, or if we want to see what's our best measurement process, we're going to have to put another instrument in the machine. So we're going to, in our machine or whatever we're using to test, we're going to get the repeatability of the best existing device, and then we're going to test repeatability and reproducibility. This can be of technicians, this can be of a process. It's just the definition of repeatability for the VIM is the same or like instrument. So if you can use the a very, very, very good load cell to do your repeatability studies, that's very stable, that's my favorite recommendation, because you can do lots of things. They often say you can kill 5 birds with 1 stone. You can do proficiency tests, you can do measurement assurance, you can do control charting, you can do lots of things with a very, very good load cell, and it can test your process to the point where I have this great load cell. I've just done tests 2 weeks ago, everything was in, and now I found something's out of tolerance. All I have to do is go back to that 2 weeks and say, hey, I know it was good here. So I only have to look at a small segment of maybe everything I've calibrated if we're running control charts and everything else. But that's highly recommended for everybody to have stable artifacts in their facility. It's just, whether you're doing ISO 376, E74, whatever you're doing, it's just going to help give that confidence, and it's going to help you with doing repeatability and reproducibility studies and quantifying that measurement process uncertainty if a similar device came in. Then we have type B uncertainty contributors: resolution of the best existing device, reference standard resolution, that's an if applicable, but reference standard uncertainty, this is usually included, but ISO 376 already includes it, so it's included in the uncertainty equation, so you don't have to deal with it. Same with reference standard resolution, that's already included in the ISO 376 stuff. Reference standard stability, often missed. Not many documents talk about stability the way they should and the way it contributes. It is usually very dominant when you do an uncertainty analysis and you type in, you look at drift from one calibration to the next. So that needs to be included. Environmental factors, and then here's the catch-all: other error sources, which Euromet CG4, as you saw earlier, gave you some additional other error sources. So if I'm going to do a Force CMC for ISO 376, I would get the calibration report for the device. I would want calibration history, because I'm going to want to test that reproducibility and the drift with time. Manufacturer specification sheet, we're going to need that for environmental. If I'm operating plus or minus 2 degrees, I'm going to have to use that equation. Other error sources, if known, go to Euromet CG4 corrections. Suggestions, and then user, depending on if you're accredited. Repeatability study, normally you're going to have to do R&R between technicians and see if there's a difference between them. The easiest thing to do there is a NOVA test, and that is built into our Excel spreadsheet, which is free to download. There's no charge. We just did this to help people with uncertainty. So even if you're curious, just go download that Excel spreadsheet and look at it. I think it can help significantly with lots of different things. So at the end of it, here's our sales promotion, and then I have what's the next webinar coming up. But implementing the adapters, you all receive the email. Implementing the adapters to ensure proper alignment and stress distribution helps with replicating the actual calibration results. And if you're paying a lot of money for calibration and then using different things, or you're using a top pad made of aluminum that you're not sending in, and then we're using a hardened steel block, that's no good. You're going to have errors galore. Our next webinar is going to discuss these errors, but in recognition of the importance of adapters, what we did is we batched a lot of adapters. We improved our process for making them. We came up with kits, commonly used kits for what we think people will use. It's not, doesn't get all cases, but it gets the majority of cases. So we came up with kits. We did a process batch, which allowed us to offer about a 20% discount on all our tension adapter kits up to 120,000 pounds. And if anybody has interest in adapters, we have a promo code ISO 376 better results. Our sales team is going to give it to you anyway, because they want to sell better adapters. Everybody here is very passionate about this, because it just improves the process, improves our overall safety. When you're making these force measurements, you're launching a shuttle into space, you're weighing uranium. Some people are weighing uranium. What's a pound of uranium going missing is problematic. It just, the whole way through, whatever your process, the measurements are usually critical enough where a 0.5% error, a 0.1% error, all these errors associated with improper adapters and not replicating how it's being used, or the calibration, will play in and have devastating impact on things. So I cannot stress enough that our passion for getting the right adapters out. So that being said, our next webinar is April 18th at 11 a.m. and it's proper adapters to reduce force measurement error. Working on this now, very excited for it. Have compiled years and years of data, years and years of testing, hoping to have like a 30-45-minute webinar, not as long as this one. And we're going to discuss the common measurement errors and how to reduce or eliminate them by using the proper adapters. And then not using the right adapters can produce additional errors that could put the force measurement device at 20 times higher than what is expected. We have examples in this presentation of errors that are 20 times higher than what is expected. So with that being said, I'm going to answer any of the chat questions, which the one I had, does Morehouse sell adapters? Yes, we do. Minimum force for calibration, is that minimum force for use as well? Yes, that is. Great question. So when we're discussing ISO 376 and the minimum use, that is the first test point. I cannot use the device below the first test point, and the classification system, whatever that classification system is, if it's class 00 at 5%, I cannot say I have class 00 at the 2% test point. So I hope that cleared that up. So it's the first test point that's tested is what that is. So I'm going to open this up. I'm going to end the recording because we're right at the hour mark for the people that could not attend. And then if anybody has any questions, please ask them now. So let me unmute everybody if anybody has. All right, so people are here with mics. If anybody has any questions, I have open dialogue and I have the window, and I can just go through. Does ASTM call, one question here, does ASTM call for a temperature controlled lab? Yes, ASTM has the same specification. The recommendation for ASTM is 23 degrees C, and it states about not varying, any calibration shall not vary by more than plus or minus 1 degree C during the calibration. But the recommendations for 23 degrees C, people calibrate to ASTM at 20 degrees. There's dimensional labs that have their equipment in there. They calibrate at 18 degrees. It's just there's a reporting criteria on the certificate. So thank you for that question. Can we get a copy of this present presentation? Yes, absolutely. I'm going to correct the error on slide 3 or 4 that I was embarrassed with, that had a class 5 instead of a class 2, but that will be there will be an email coming out with PDF So I'm going to correct the error, and then we're going to send that out later today. We'll upload the webinar if anybody wants to watch it. We'll upload it. Yes, presentation will be emailed. So um, will there be a link to review what I missed? Yep. Yep. Beginning of the webinar, link, PDF, whatever way you want to do it. Again, I'm here for questions. If someone wants to call or email, if something comes up later tonight and said, what's the difference between E74 and 376 in accordance with, timing or something, whatever. Happy to answer questions. How will you ensure the particularity of loading in a tensile mode? Ensure the particularity of loading in a tensile mode testing. Well, the goal there, I believe hopefully I'm understanding the question correctly. In tensile mode is having the two sphericals. So if there is any misalignment, having those that ball seats and ball cups, the sphericals, that it will find center. So if the top is out a little bit and the bottom, but then the bearing pad test for you said tension, but bearing pad tests and compression will tell you the actual error of the cells. In further talking to that point, different cells behave differently. An S-beam cell, if people have used them, the S-type cells, they are very sensitive to rotational errors. Any misalignment on those cells and you would have very large errors. So by using the right adapters, you can help eliminate those. And unfortunately, what ends up happening, which I don't like, is in our lab, we calibrate an S-beam cell with our tension adapters with two sphericals per the ISO 376 Annex recommendation, and we're going to get better results than the person that's going to then use those out in the field with threaded rod. But that's what we do. We're using those adapters. We want to replicate use, but again, at the same time, if we're not getting tension adapters, we're going to use ours and give the best possible measurement result possible. So hoping that people go out in the field and take notice and then use those types. If it's a small force, I've seen people use bearings, rod end bearings, and some other things, and get very good results. So it just to ensure that there are no eccentric forces. Oh, perpendicular. Oh, thank you. So yeah, hopefully I answered that on that perpendicular. Some of it's going to be based on the machine. The adapters are just going to help compensate for some of the side load that can happen because of the machine. So yeah, thank you for everybody for the kind words as well. I see those. I have another question coming in. Have you completed tests with your tension adapters in a horizontal plane rather than vertical? No, we've been asked that a lot. Horizontal force testing is very difficult. We could do it in a cal machine. The only time we've ever done horizontal testing is when we ship big cal machines and we need to proof load them before they go out. Sometimes we assemble them horizontally because they're so big, and we do proof testing there. So we have not done numerous tests. The proof testing we're confident with because we only need to be accurate to within 10%. So that's not a big deal. But in general, horizontal is going to give you different than in the vertical plane because you have the weight of several things on that force proving instrument. So I would like to do more testing vertical versus horizontal. It's just we just can't make a vertical horizontal dead weight machine without some serious effort, pulleys, and some other stuff that then would then be questionable as well. So, but yeah, thank you for that question. We've considered that quite a bit. I'd like to do the other thing we could do is make a cow machine and then turn it, but we're going to have the same thing. We're going to be fighting. We're going to be fighting a lot as to keeping having a frictionless force in the horizontal plane is very, very difficult, and that's really the fight. You're going to have some friction, so I don't know how you're going to account for that error. There's probably some ways, and some people have probably done it. Is there an issue with testing load cells and tension horizontally? We use our cell horizontally in our facility. It's something you're going to have additional errors for horizontal. Like I said, there's no way you're not going to have additional weight. if you think of this, the only thing I can say is if you think about a torque load cell, lots of people put arms on torque load cells. Well, as soon as you put an arm on a torque load cell, if you do not support it, you have an overhung moment. So when you're in the horizontal, you have some of those overhung moments on the cells that you have to overcome before you start to see stress. Now, whether a lot of that error is just down in like 0 to 2%, that's what I'd like to know. I suspect that each load cell is going to be different. Alignment's going to be critical. And I also suspect that if you get everything right, the error is going to be minimized at below 10% of the range. But I would be very skeptical using cell horizontally at low forces. I know the one application is rocket thrust stands are used a lot in the horizontal position because they fire the rocket there, but they usually have lots of frictionless. They usually have a system that is fairly frictionless, and the errors are quite low. So maybe look at your system and see how alignment of everything, see if there's any friction issues, see if everything can slide well in tension would be my suggestion. Any other questions? Mics are open. So we're a cable testing lab, and that is why they're horizontal. Yeah. Cable tensiometer or just cable. Yeah, I've seen that. So you're most likely doing large forces. If you're testing cables, the other cable testing is tensiometers, but that's an entirely different thing. So no, I've seen a lot of horizontal testing machines. So it seems that that's the only way to really do cables that well when people do not have the height. So yeah, again, I get a lot of thank yous. Thank you for attending. Your time is valuable. I certainly appreciate lending your ear to listen to me talk. So thank you. Thank you all. If anybody has any additional questions, let me know. I'll hang around for a minute or two. Some people are dropping out, and then we'll get this recording up on the web for those that came in late, and we'll get PDF sent out. And with that, if there are no other questions, I thank you all. Have a great day. And if one pops up in a minute, I'll answer it. If not, feel free to call, email, do whatever you want. So thanks. Hopefully some of you learned more about ISO 376 today.
Wireless, USB, and data logging solutions.
Huh.
An internal amplifier.
Okay. There's a sales pitch. So, all right. So yeah, thank you all. Type this in if you. I'm going to end the session. If questions come up, let me know later. So thanks everybody.